Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, leading off, we're going to summarize some of the top stories in science. Well, let's just jump right into some of the top stories of the past week. Our lead story today concerns the sky. Is the sky falling? Well, no, we don't have to be Chicken Little. However, there is an 8.5-ton Chinese satellite that is going to plunge back into the Earth sometime between March 30th and April 2nd. Now, you know that using Newton's laws of gravity, we can accurately calculate what it would take to shoot a space probe right through the rings of Saturn. That's how accurate Newton's laws of gravity are when applied to the trajectories of space probes. But why can't we calculate where this gigantic 8.5-ton satellite is going to land? And that's because it's like skimming a stone on the surface of a pond. You don't really know how far the stone is going to go because each time it impacts on the pond, well, the equations are quite complicated, and it's almost impossible to tell exactly how far the stone will go as it skips across the surface. In the same way, as the satellite orbit decays, it's going to gradually hit the atmosphere of the Earth, the outer shell of the atmosphere, and like a skipping stone, it's going to go back and forth, in and out of the upper atmosphere. Each time it does that, the trajectory is unknown because it's simply too difficult to use Newton's laws of motion to calculate exactly how far the satellite will go on each bounce. This means that, yes, between March 30th and April 2nd, some people will have a light show as they see this gigantic meteor streaking down from outer space. Now, for the most part, let's be fair, for the most part, the Earth is covered 3/4 by water, and therefore most scientists believe that the satellite will land harmlessly in the ocean. However, there's always a chance that it could land on the remaining 25%, including somebody's backyard. Now, believe it or not, these satellites have actually come down perilously in the past. For example, during the days of the Soviet Union's rivalry with the United States, the Soviets sent up a satellite containing radioactive uranium, and it had an orbit that decayed, and it slammed into the northern territories of Canada. Well, you can imagine the CIA saw this as a bonanza, and so it sent teams to search for the wreckage of Cosmos 954, a Soviet satellite which plunged into the northern areas of Canada. Skylab also came down, an American satellite. It did not have a nuclear reactor on board, but it created quite a controversy because people were guessing as to where the American satellite Skylab would eventually come down. Now, to be fair, we should also point out that eventually almost all of our satellites will come down. In deep space, there's very little air friction to deal with. However, there is a little bit, and as time goes by, as the decades, centuries, and millennia go by, these small little perturbations build up. And so this means that, well, yes, it means that our satellites will eventually come streaking down on the planet Earth. However, don't hold your breath. It may take centuries to millennia for some of our satellites to eventually come down to the planet Earth. And also, of course, last month, my colleague Stephen Hawking died at the age of 76. Not since Albert Einstein have we had such a towering figure in physics who could not only probe some of the deepest secrets of space and time, but also mesmerize the public about the mysteries of this great universe of ours. Well, now, of course, after a month, people are beginning to wonder, what was the lasting legacy of Stephen Hawking? There was a Hollywood movie about his life called The Theory of Everything. However, that movie did not answer the key question. First of all, what is the theory of everything? Nowhere in the movie does it actually mention what this theory is. And second of all, did Stephen Hawking really attain the theory of everything? Well, let's go back. When Einstein was alive, he spent the last 30 years of his life chasing after a theory of everything that would unify the two great theories of modern physics. The first is the quantum theory, the theory of the very small, the theory of the atom that makes possible lasers and transistors and iPhones and iPads and all the wonders of modern technology. Then we have the other great theory, the theory of the very big, and that is relativity theory, the theory of Albert Einstein. Now, the goal of Einstein was to create an equation perhaps no more than 1 inch long that would unify all the laws of physics into a single theory. That is the theory of everything. Now, think of the equation E equals mc squared. That equation is half an inch long, and that allowed us to unify energy and matter to explain the energy source of the stars. Why do the stars shine at night? Because M, that is hydrogen, is turned into E, and that is energy. And so the matter of hydrogen turns into the energy that drives the stars. And so Einstein wanted a similar theory that would explain everything. Gravity, the electromagnetic force, the wonders of the world we see around us. But unfortunately, he failed. Now, what Stephen Hawking did was he began to pioneer the first application of the quantum theory to Einstein's theory in the form of black holes. We know that black holes are the end product of stellar evolution. A dying star, a massive dying star, will eventually decay down to a black hole, and it is black because its gravity is so intense that even light itself cannot escape. Now, what Stephen Hawking did was he showed that when you apply quantum mechanics to this black hole, it's really gray. That is, it emits radiation called Hawking radiation. So black holes are gray, not black, and eventually they lose so much energy that they explode. Now, this was revolutionary because before we had never applied quantum mechanics to a classical problem like a black hole. However, that's not what we're getting at today. Today we're going to talk about the lasting legacy of Stephen Hawking. And even though he set the agenda, even though he paved the way by showing that, yes, you can apply quantum mechanics to relativity, you can calculate quantum corrections to a black hole, that leaves open the question, is that the theory of everything? And the answer, unfortunately, is no. You see, to create a theory of everything, you have to quantize gravity itself. Now, what does that mean? Take a look at light. When you quantize light, that is, you apply atomic physics to light, light becomes a collection of particles. These particles are called photons. A photon is a particle of light. And so we now have a theory of quantum photons, and that theory is called quantum electrodynamics, perhaps one of the most successful theories of all modern physics. Everything you see in your living room is a byproduct of quantum mechanics combined with transistors, lasers, iPhones, iPads, all of that coming from the quantum theory. Now, the question is, when you quantize gravity, in the same way as you get photons when you quantize light, you get gravitons, particles of gravity. Now, to be fair, we have never seen particles of gravity in the laboratory. They're much too small. But you can calculate what happens when these particles of gravity bump into each other. Now, with photons, we know how to calculate that. In fact, Richard Feynman was one of 3 physicists who won the Nobel Prize in Physics in 1965 for explaining how you calculate what happens when photons bump into other photons and electrons. Now, here is the problem. Here is the key. When gravitons bump into other gravitons, or when gravitons bump into electrons, and you calculate what happens, the whole theory blows up in your face. It yields nonsense. Instead of giving a reasonable answer as to why you're sitting in your chair, the mathematics says you explode. Now that, of course, is ridiculous. That simply means the theory is incomplete. Now, how did Hawking deal with this problem? He believed that the solution was string theory, but because of his illness, he was not capable of working in this field. So here we have the problem. We have a theory which can, in fact, calculate with gravitons, called string theory, but it is untestable with present-day equipment. So, in some sense, we have a theory of everything. It's called string theory. In fact, that's what I do for a living. That's my day job. However, testing it is a problem. So in other words, Hawking could not get the Nobel Prize in physics for, well, several reasons. First of all, Hawking radiation, the radiation of a black hole, is so faint that you cannot detect it with instruments. It's hard enough even detecting the radiation from a black hole, let alone a gray hole. And so that means that he could not win the Nobel Prize for the discovery of Hawking radiation, even though every physicist I know firmly believes that Hawking radiation is real and not imaginary. And second of all, he could not calculate what happens when gravitons bump into other gravitons. That is the key to the whole puzzle. So, when Stephen Hawking was 21 years old, famously, he received a death warrant from his doctors. His doctors told him when he was 21 that he will eventually waste away, become paralyzed, and die of ALS. That's why he began to focus on some of the biggest problems in all of physics. The biggest problem is to complete Einstein's original dream. However, in this sense, he failed. He set the agenda. He pointed the way. He made contributions, but a complete theory of everything still eludes us. So, if you are 21 years old and you're looking for something to shape your life and destiny, perhaps you may seize upon this problem to give meaning to your life, and perhaps you will complete the dream set into motion by Albert Einstein himself. I just finished a national book tour traveling through San Francisco, Los Angeles, Chicago, Washington, Philadelphia, Boston, you name it. I was there signing perhaps your copy of my latest New York Times bestseller, The Future of Humanity. During the tour, I collected a number of questions that people had concerning my book, and I'd like to spend a few minutes in the remaining minutes of exploration to answer some of these questions that you raise. One common question that I got is, let's say hypothetically that we do go into outer space, but what about the problems on the Earth? What about global warming? What about hunger? What about all the potential problems of pollution and overpopulation? Well, let me say right now that we should not go into outer space to escape problems on the planet Earth. We are Earthlings. We are on a spaceship. The spaceship is called the planet Earth. And we have a responsibility to make sure that we don't blow it. That's why global warming is real. It's not a fiction. No matter what the skeptics say, it is real. The Earth is heating up, and human activity is driving much of it. And so we have to clean up our own act. We don't want to go to Mars and ruin Mars as well. We have to clean up our own act. And this is a political problem. It's a problem that we can only solve, not just scientifically, but politically on the planet Earth. Now, another question I get is the question of, well, a Mars colony. We're not talking about evacuating the Earth to put the population of the Earth on Mars. No. We're talking about a small settlement on Mars. And won't it be expensive, some people said. I mean, after all, every screwdriver, every hammer has to be brought from the planet Earth to Mars. And won't that bankrupt the country? Well, the short answer is no. Because once the settlement is created, the goal is to be self-sufficient. So you don't have to have an umbilical cord from the Earth to Mars in order to feed and cultivate the civilization on the red planet. So how does that work? First of all, energy. You need energy if you're going to go on Mars, and that's where solar panels come in. If you saw the movie The Martian, you realize that, yes, the solar panels would have to be quite large, but you can, in fact, generate power on Mars using solar panels. Second, what about mining operations? It turns out that the soil of Mars can be duplicated on the planet Earth. We know what Martian soil is made of. We can duplicate it on the planet Earth, and we've shown that we can make brick. Bricks can be made out of Martian soil. And so we can begin the process of creating buildings and factories on Mars. And second of all, what about mining operations? One of the first things you're going to mine on Mars is ice. Mars has plenty of ice. If there's one thing Mars has in large quantities, it is ice, either at the polar ice caps or underground in the permafrost. And it means, therefore, that you can extract drinking water. You can purify the ice, to create drinking water. You can separate out oxygen and hydrogen from water, hydrogen for rocket fuel, and oxygen for breathing. And then, of course, you have to eat. You don't want to have to bring all the food from the Earth all the way to Mars just so you can have lunch. No, you want to have a self-sustaining agriculture. And that's where genetic engineering comes in. Genetically engineered algae, for example, can thrive in the atmosphere of Mars. And so it's possible that we could get mining operations off the ground. It's possible that we could begin to create a self-sustaining colony on Mars. And again, no one is talking about evacuating the Earth to go to Mars. No, we're talking about an insurance policy, a settlement on Mars that will eventually become self-sufficient. And that's the key. So it is not going to be dependent upon the Earth for supplies. And another question I got during my book tour is, well, let's say we go to the stars. How are we going to do it? Are we going to send Captain Kirk to the stars? And the short answer is no. The way to go to the stars is, first of all, to send postage-sized chips to the stars. And this is a proposal spearheaded by, well, physicist Stephen Hawking. The idea here is that Silicon Valley billionaires have all this money and they want to do something useful with it. And their design is to create a postage stamp that has all the sensors on it, suitable to take pictures of extrasolar planets orbiting distant stars, and put them on a parachute and shoot them in outer space with a laser beam. So the laser beam will be energized by about 100 trillion watts of power using known technology. We're not talking about science fiction. We're talking about using known technology to create a postage-sized stamp that could then be sent to the stars. Now, this does not sound so far-fetched because we're talking about off-the-shelf technology. We know a lot about lasers. We know about outer space. We know a lot about computers. You put the three together and bingo, you have a starship. Now, this is not going to look like the starship you see in the movies. We're not talking about Star Wars or the Millennium Falcon or anything like that. We're talking about the first probes. And when will the first probes be able to go to the stars? Perhaps by the end of this century. So we're not talking about anytime soon, but it'll take a few decades to get the resources and money. So far, $100 million have been pledged to create this. Now, sometimes I get emails and notices from people that I met during my book tour who say that, well, they're convinced that the aliens are out there. We don't have to visit them because they visited us. And when I ask them, how do they know that? They say, well, it's because they've been abducted by aliens from outer space. They've been in their flying saucers. They've been abducted by aliens from outer space. So my personal point of view is, if you've ever been abducted by aliens from outer space, then for God's sake, steal something. I don't care what it is. An alien chip, an alien paperweight, anything. Anything so you have bragging rights, so you can say that, yes, you were in a rocket ship from outer space. And not only that, but there's no law against stealing from an extraterrestrial. I mean, think about that. Think of all the laws that we've created on the Earth. There is no law that says you can't steal from an extraterrestrial. And so, a word to the wise. You want to have something tangible, because science is based on things that are testable, falsifiable, and reproducible. Hearsay, well, maybe you're correct. However, who's going to believe you? Maybe it was a dream. Maybe you got drunk that day. Maybe you're a liar and just want to get your name in the newspaper. Who knows? The point is, unless you have hard evidence that's testable, reproducible, and falsifiable, no one's going to believe you. And speaking about that, let me just say a few things about how we can test some of these theories. For example, Bigfoot. Some people email me or come on my radio show and ask me about Bigfoot, and I tell them that, well, scientists have actually analyzed the hairs and the DNA of the footprints that were left behind by a creature, many people think were left behind by Bigfoot. Well, just a few months ago, scientists analyzed the DNA from one of these footprints. And what did they find? Bingo. The DNA of a bear. In fact, this is something that scientists have said repeatedly over many decades, that many of the sightings and many of the footprints and the hairs that are associated with Bigfoot are actually those of a bear. And so, once again, we have a reproducible piece of evidence. Now, does that clinch it? And the answer is no, because you cannot prove a negative. In other words, you cannot prove that unicorns don't exist. I mean, think about it for a moment. Even though we have scoured the earth looking for unicorns, maybe, just maybe, there's an island someplace in a cave that no one has ever explored where unicorns thrive. You can't rule it out. So in other words, it's impossible to disprove a negative. Or, for example, you cannot disprove the existence of God. There's some atheists who say that, well, we can disprove the existence of God. Well, no, you cannot disprove a negative. Just because you have an experiment today that seems to indicate that there's no celestial being in outer space, it doesn't mean that tomorrow you can't have one. And so that's the name of the game. Science is based on things that are testable, reproducible, falsifiable today, but who knows about tomorrow? So my personal attitude is, even though we can debunk many so-called myths, we have to keep an open mind about certain things. And speaking about keeping an open mind, perhaps you've seen the Atta skeleton. You can Google it on the computer, ATA skeleton, and it looks remarkably like an alien, something straight out of a movie. First of all, it's a small skeletal fetus. It's roughly 6 or 8 inches long, very tiny, but my gosh, when you see it, your jaw hits the floor. It has a long, narrow head. It has big, bulging eyes. It has a small, diminutive body, something right out of a science fiction movie, something right out of a book about Roswell, for example. So many people say, aha, here is the proof. This decades-old skeleton found in Chile shows that, yes, we now have reproducible, falsifiable, testable evidence about aliens from outer space. Well, just this week, scientists decided to take up the challenge, and they tested some of the DNA of the fetus. And what they found was, ta-da, it is a human fetus. It is not an alien. It turns out that all the genes there are human genes. However, the genes are horribly mutated. In fact, some mutations were seen in the skeleton that scientists have never seen before. So, after everything is said and done, what was the final conclusion by these geneticists and scientists who did a detailed analysis of the Atta skeleton? Their basic proposition is that it was the chemical industry, that is, nitrate farming in that area decades ago, that probably contaminated several of the members of the local population. And so this fetus was born aborted. It was a spontaneous abortion, and it was not viable. It could not survive in the open, and as a consequence, it was deformed, and we now see the evidence of the deformations. And by golly, it really does look like one of the aliens you see in a science fiction movie. That's why many cult magazines have said that, yes, this is final proof that the aliens have in fact landed on the planet Earth. Now, does that mean that we have never been visited by aliens from outer space? No. It simply means that so far we've seen no reproducible, falsifiable, no testable evidence of such a visitation. Could such a visitation have happened in the past? Sure. In fact, Carl Sagan even wrote about the impact of what might have happened thousands of years ago if an alien civilization did land on the planet Earth. And it sounds like something right out of a Hollywood movie script. So that cannot be ruled out. However, this skeleton can, in fact, be ruled out. So, in other words, I don't share the attitude of some of my colleagues in the scientific community. They roll their eyes, they start to giggle and laugh, and then, well, we call this the giggle factor. That is, scientists are inherently skeptical about these claims. Now, that is a good thing. However, I think if we're so skeptical that we dismiss all these claims, I think that's going too far. In the spirit of science, we should be open to the idea that even crazy things may happen at some point. But as Carl Sagan once famously said, remarkable claims require remarkable proof. So in other words, we should be open. We should be open to the idea that there are, in fact, remarkable claims that, well, who knows, may one day turn out to be true. But remarkable claims require remarkable proof. Good day.